So, just like before when we used the concept of work to develop a formula for the kinetic energy, now we want to do the same with a different form of energy, gravitational potential. Now, besides storing energy in a system in the form of movement, aka kinetic energy, we can also store it in its relative position to the Earth's surface, and that is known as gravitational potential energy. It might be a little less obvious than kinetic energy because you can't really see the effects of potential energy directly. But let's do what we did before with kinetic energy, okay? We're going to start by observing what an object does naturally before adding in an unnatural component from the environment to do work on it. Okay, let's set up our scenario here. We have a ball in the air, and you know that if you just leave it like that, it's going to have a force of gravity acting on it that will cause it to accelerate downwards. Right, boing, boing, boing. But let's reach into the picture and apply a force of equal magnitude in the upwards direction to balance out the amount of force that gravity is exerting on it. So now we can say the ball is either at rest or moving at constant velocity. We're going to say it's going to move upwards at constant velocity because we don't want to deal with negative signs and whatnot. We're going to move this over a displacement actually, of delta d, and this will be the position, the final position, and this is the initial position. Okay, now the stage is set. So you see this force over here that we've applied as part of the environment applying on the ball, and this displacement are in the same direction, right? That means the degree between the force and the displacement will be 0, and cosine 0 is 1. And that tells us that the amount of work done is the force we applied multiplied by the displacement. Now we know that the magnitude of this force is equal to the magnitude of the force of gravity. Then what is the magnitude of the force of gravity? Well, that's mass times the gravitational acceleration constant, which you already know as 9.81 meters per second squared. And so let's slot this into the formula. And what about this? We can break this down some more. Delta, the displacement, will be the final position minus the initial position, right? We said up was positive, remember that? And now let's open up this bracket. We will put this, multiply that in here, and multiply that into here. I've changed the color here, I hope you don't mind. Now this position, usually we use the symbol h instead of d to signify that it's a height above the ground, right? So let's replace that. Okay, since we're not changing the kinetic energy, in this case the amount of work we did is equal to the amount of potential energy that we gave to the system. And so mathematically, we can also say, write it as like this. So you see that's the final potential energy minus the initial potential energy, and the difference is equal to the amount of work we exerted. And once again we see we have matching terms just like with kinetic energy, and that tells us that the formula for the potential energy of an object is given by this. Now this h term over here gets a bit tricky, and we'll talk about this right now. Let me rewrite the formula once again for potential energy. Many students just assume that this h over here is a height of the object above the ground, right? But that doesn't necessarily have to be so. Let me give you an example. Say a 10-kilogram dinosaur is terrorizing a table, roar, by standing on it. If the ground was our reference point, then the dinosaur's potential energy would be the mass, that's 10 kilograms, times 9.81 times 1 meters. That gives us 98.1 joules. That means the dinosaur has a potential energy of 98.1 joules relative to the ground. But if we set the reference point as the table surface, now h will be equal to 0. So the dinosaur has 0 potential energy relative to the table surface. And we can even go a step further and say our reference point is a meter above the table surface. In that case, the dinosaur's potential energy would now be negative 98.1 joules. So it's no longer height above the reference point, it's now a height below the reference point. So the point is, the value of this potential energy depends on our point of reference. So an absolute gravitational potential energy is meaningless. It's only relative to a reference point. But then when you change the question into what's a change in gravitational potential energy, for example, if a dinosaur jumped off or jumped on or something like that, well, that will be the same regardless of which of these reference points you choose. So I hope you got that. So now you know, if a teacher praises you by saying you have so much potential, you shouldn't get too happy. You should be asking her, relative to what?